So, uh, so let's get started on today's class seminar. Today's speaker is Dr. Vedran Brdar, and he will talk about the non-oscillatory exploration of MiniBooNE access. So please start.
Thanks a lot for the invitation to give this seminar. Yeah, I'll be talking about the limits on the non-oscillatory explanations of MiniBooNE access, which is based on recent work with Oliver Fischer and Alexei Smitnov, who are together with me at Max Planck for nuclear physics in Heidelberg. But before I start on MiniBooNE, I need to talk first a little bit about LSND. That was the first experiment that has reported the anomaly, basically the excess of electron antineutrinos in the beam of muon neutrinos. And they have, like 20 years ago, reported this 3 sigma excess at the baseline over energy at the order 1 kilometer per GeV. This is their money plot, where you can see the usual events from antineutrinos in green. Their other stuff that is also standard model in red, and this data which clearly rises above the green and red regions. The blue is not the measurement, the blue is only the fit to this axis. So this kind of deviation from standard model have been there already since early 2000s. And then following the LSND result, they decided to build a MiniBooNE detector at Fermilab site to see, basically to test the LSND. What MiniBooNE has actually reported is basically a new anomaly, essentially, because they measure this low energy excess. I took this picture from the most recent MiniBooNE result before Neutrino 2020 conference. You can see here the deviation between the data and the standard model predictions. Just statistically, they're reporting 4.8 sigma at the moment. And when you combine this in quadrature statistically with the LSND, which is around 3.1, you get something that is 6 sigma. This is kind of very impressive. It's not a smoking gun for BSM. It could also be explained if they're just not very good in handling their backgrounds. So the picture is still unclear, but the new physics scenario has not been excluded, and in fact there have been several proposals in the last few years how to address that. I'm here also showing the table from the most recent MiniBooNE paper, where you can see the number of events for all these background events. In particular, you can see here the most relevant contribution here is from pions, misidentification of pi zeros. Then the next relevant one is coming from the decays of delta resonances. That's here in yellowish. And there's also the usual electron neutrino contributions, which are here in this stacked histograms showed in these shades of green. So MiniBooNE is basically reporting this electron-like event excess. So basically single showers and single electromagnetic showers. And later I will discuss several realizations. But first, now I'm jumping to the BSM right away. So given this anomaly, it's a question how to resolve it via new physics. And the most simple and most elegant solution, something that is usually employed, is the electron volt scale sterile neutrino. That one has been used also for solving the reactor anomalies, and also the MiniBooNE paper itself has fit to this kind of realization. In this slide, I'm just going to argue that this solution is not very successful, and then in particular, one would have to go a bit beyond this kind of framework to explain the MiniBooNE. So in the previous slide, I argued that the axis should be around 1 kilometer over GeV, and from the measured mass square differences that we know between the active neutrinos, the oscillation maxima arises at much larger baseline over energies, basically at around 500 or 1500, depending which of these two you take. So basically, you cannot explain some, you don't have efficient oscillation at 1 kilometer per GeV where you would see an excess. And therefore, this calls for introduction of another mass square difference if you want to do it via oscillation. This mass square difference should be of the order 1 electron volt squared, which is easy to see from the standard neutrino oscillation formulas. And this basically means that you need an extra EV scale sterile neutrino, the popular so-called 3+1 scheme. So in the left panel, I'm showing this result from the global fit of Kopp et al., where this is basically the appearance of electron neutrinos in the beam of Moore neutrinos. You can see here the LSND preferred in this light gray, sorry, what is this, orange. And in this darker shade, there's the MiniBooNE, and combined is in red. You see that this red region is basically evading all the constraints from Opera, Icarus, NOMAD, and all these other experiments that are here shown on the plot. So it looks so successful if you just look at this channel. But if you add an extra sterile neutrino, you basically, you have two new parameters, the mixings between sterile neutrino and muon, and mixing between muon and electron, if you want to go from muon neutrinos to electron neutrinos. And therefore, you have also the constraints from the reactor experiments, which constrain the sterile neutrino mixing with electron neutrinos. And combining that information with the left panel here, you end up with the following plot here in the when considering the muon neutrino disappearance searches. It turns out that that channel is basically excluding the preferred regions for MiniBooNE and LSND very significantly, and the most important experiments for that are MINOS and the IceCube, which are giving these limits. So in principle, it would work, but the global neutrino data is just suggesting that the most simple addition of electron volt scale sterile neutrino is not consistent with the data, and one actually would have to go to alternative models. And in the next two slides, I'll try to basically show what all the work that has been done. There are not too many papers, but there have been some qualitatively different studies. The foremost and most important thing is that the MiniBooNE sees one shower events that can be produced by electron, photon in the final state, or collimated electrons, E plus E minus, or collimated gamma gamma. So all of these four possibilities could work to explain these extra electromagnetic showers, because MiniBooNE cannot distinguish between electrons and photons. So this survey of these non-oscillatory explanations, I start with a model by Gninenko from 2009, who used the upscattering of muon neutrinos into 100 MeV scale right-handed neutrino, and then the right-handed neutrino further decays into photon. This is illustrated here. You can see the production through interaction with active neutrinos of right-handed, and that guy later decays into active neutrinos and a photon. So for this scenario, the mixing required between muon neutrino and sterile is around 10 to the minus 3. And the magnetic moment that you need is of the order of 10 to the minus 9 or so in terms of Bohr magnetons. The next model, the next sets of models were only proposed after MiniBooNE updated the original anomaly in 2018. The paper by Bertuzzo discussed the upscattering of muon neutrino into 100 MeV right-handed neutrino, so the same as Gninenko. It's just that this process, unlike the one in this previous model, is coherent instead of incoherent. And the decay of right-handed neutrino is also different. it goes to neutrino and Z prime that is on shell, and then Z prime further decays into E plus E minus. If these E plus E minus are very collimated, they will give single shower events in MiniBooNE and can basically explain. So they're basically this signature here. Simultaneously with this paper, there was another paper which basically employed the same particle content. It's just that they didn't decay the right-handed neutrinos in the Z prime, but instead they used the three-body decay through the exchange of Z prime. Three-body decay into neutrino, E plus and E minus. And again, E plus E minus could give a single shower if the angle between these two is rather small. This realization gives distributed decay gives longer lifetimes, but this of right-handed neutrino, but it still works. The next model is something that appeared toward the end of last year. This is one of my collaborators from this project, Fisher et al. They flipped the story. So instead of producing the right-handed neutrinos in the detector and let it decay into something that gives a shower, here the strategy is to produce the right-handed neutrinos in the source, in the decay pipe of the detector, and then that right-handed neutrinos travels to the detector and decays inside of the detector into something that gives a shower. Production-wise, similar, but qualitatively different are also papers by Dentler et al. And De Guea et al. From last year, where the N is also produced by mixing in the decay pipe of the experiment. But instead of letting the right-handed neutrinos travel and then decay in the detector, they actually they decay promptly into active neutrinos and scalar, and then this active neutrino can just go in the detector and do the usual charge current upscattering into electron neutrino through the through W, and this will basically give you the extra signature, the extra single showers. Then there's models by Data et al. And Duta et al., very recent ones, where they use the scenario of Bertuccio from previous slides, but with the crucial difference that they swapped the Z prime with the scalar. That's relevant because the MINERNA limit that was probing this model quite strongly is very much relaxed if you use scalar, because the cross-section of the process drops very much at the energies where MINERNA operates. And this is the last but not least by Abdallah et al., where you can see the production of new scalar, again in the process where active neutrino goes into sterile. In this case, sterile neutrino doesn't do anything, but it's this scalar that gets radiated from the propagator through this gauge-cage scalar coupling. The scalar can basically decay into E plus E minus pair and again give a shower. So this was the brief overview of all the possibilities that have appeared in the literature. And now I'm just, at least the possibilities to the best of my knowledge that appeared, the phenomenological scenarios. There were more models, including extra dimensions and breaking of Lorentz invariants and such things. But here I'm basically considering these cases where there's a particle physics process involved. And now the question is whether all these models that have been proposed, mostly in the last 2 years or so, is that everything? Do they cover everything? Are these models constrained? Are they maybe excluded? Is there more models that could be written up? What is the actual new physics scenario? What is the new physics situation when it comes to MiniBooNE? This was the motivation for our work. And we wanted to basically systematize, do a systematic survey of all these possibilities. And basically, in that sense, constructing the kind of sort of an effective theory of MiniBooNE. I'm starting here, in doing so, I'm starting from two very basic assumptions, not assumptions, these are the facts. So in the source of events are protons from the booster that hit the beryllium target and producing secondary particles. This is on this left edge of this equation. So it's just the proton nuclei interactions. And then we also know that there is a certain excess of single showers in this 818-ton liquid scintillator that MiniBooNE employs. Yes, they find these extra single shower events. So what connects these two well-known features? So proton collisions on target and these excess events that are seen as one shower. So I put it here as a black box. And in principle, that can be a single new particle or certain system of particles that basically leads you from this interaction to the excess of events. In principle, you can add here many items that give the X, many sequences, many items. At some point you would have certain suppression and you would not be able to explain the anomaly, especially if you ask for the several interactions to take place. So I'm going to be here very minimalistic and basically basically consider the scenario where the number of new physics new physics vertices would be more correct to say, between this proton nuclei scattering and the excess of one shower events would be minimal, so 2 or 3 at most. And I'm going to divide this X, this black box, into XS and XD, where the former one would be associated to the source and the latter to the detector. So what is this new particle that you can produce in the source? How can you do it? Option number 1 here, that is scratched, and I will tell you later why, is in proton nucleon collisions, you can just immediately produce some new physics, for instance, some right-handed neutrino. In principle, it's an option. Option number 2, after following this proton nuclear collision, you produce pions and kaons and all these other heavy mesons. You can also produce new physics from decays of these particles. And the last but not least, from active neutrinos, and basically the muon neutrinos, because they have the strongest fluxes, you can produce right-handed neutrinos or some new physics particle, for instance, just from the mixing. These are the 3 options, and now I can tell you why I scratched the first one. In the first slide, I showed you that the excess, I can just go back. You see here the excess in neutrino mode is around 500, whereas the excess in anti-neutrino mode is 77. So it's a huge asymmetry. If really the interactions of protons on target would be responsible for the new physics, you would not expect to have any real difference between these 2 modes, because the number of protons on target in these 2 modes are more or less the same. This is why I'm scratching this one and not bringing it up again. And I'm left with these 2 options, meson decays and neutrinos as source of new physics at the source. In red, I wrote here, this particle need to be charged. So neutral pions and kaons would not work, even though you can in principle produce some new boson, for instance, in neutral pion decay. The reason why neutral particles don't work is because MiniBooNE also has performed a dark matter search in their beam dump mode. And in that mode, the fluxes of neutral mesons are very similar to the fluxes of neutrinos. Very similar to the fluxes of neutral mesons in the neutrinos and anti-neutrino mode. So they haven't found anything in that beam dump mode. They're hoping to see some signature of some dark matter or some new scatterings. But since they didn't see anything, this means that also these pions are not inducing any significant new physics events in this neutrino and anti-neutrino mode that we're discussing here. So finally, to summarize this production here, the new physics can arise either from pion and kaon decays or meson decays, charged meson decays, or from neutrinos through, for instance, mixing. So these are the two options. And then in the detector, something that connects to this right side to give showers, you have some new physics leading to some particle that would give a shower. So either gamma electron or this gamma gamma or electron electron pairs that are collimated. Here, for simplicity, I'm just showing the cases for right-handed neutrinos that I'm going to discuss throughout the talk. But for bosons, it would also hold. It's just that the model building situation for gauge boson and scalar bosons would be a bit different. But qualitatively, it's the same. So first option is that right-handed neutrino decays into a particle Xi, and with Xi, I'm going to label all these classes of particles that can directly give an electromagnetic shower. So electron photon, electron positron pair, and gamma gamma. So option number one is direct decay into such particle, and that can, for instance, be this decay of right-handed neutrino in the gamma and the neutrino, or decay into a neutrino plus electron positron. The second option is where right-handed neutrino doesn't decay directly into such particle Xi, but instead it's sequential, two-step process where it first decays into some boson, and then the boson later decays into, for instance, C plus C minus or gamma gamma into something that can give a shower. So two-step process. The third option is where the right-handed neutrino would just decay into electron neutrino, and then this electron neutrino would later upscatter in the detector and give electrons through just the usual standard model interaction via the exchange of W boson. There's also the option that N can scatter, but this scattering would introduce some extra smallness because of the new physics couplings, and N also is produced with the suppressed branching ratios from the pion decays, which is also small. So there are basically two smallness here. I'm not saying that it couldn't work. Maybe one can think about building a model, but this kind of option will be kind of next to leading order in the organization, how I want to classify the scenarios. So to summarize here, I have two options for XS and these three options for XD. And in the next two or three slides, I'm just going to go through this combination of these two and these three. So there will be 6 different possibilities. Okay, so the first one, the first scenario is mixing decay. I'm going to have the abbreviations for this scenario as M will stand for mixing and D for decay, and later U for the upscattering. So this is the scenario where the heavy neutrino is produced from the kaon and pion decays through the mixing, and then the right-handed neutrino just decays in the detector into something that directly gives a shower. This is the schematic representation, and when you look at the formula for the event rates, it's important that what appears is basically this exponential here, which tells you that the right-handed neutrino produced in the source should travel for the distance for the distance of the order of the baseline, and then decay within the detector that has the length d. So this factor here is also coming from the expansion of the exponential, actually 1 minus exponential. This d multiplied by the area of the detector that is here in front gives you the volume. So basically in this scenario, you don't need to scatter, you just produce N in the source, and N needs to decay in the detector, so it's the volume that matters, not the mass of the detector for the number of events. I put here in blue this epsilon and F. These are two relevant factors, not just for this scenario, but in general. By epsilon, I'm quantifying the various efficiencies, and the F stands for it's basically the number that tells you what fraction of events is one shower. If this psi is, for instance, photon, then you only have one shower, and then F is 1. But if your final state is electron positron, then this electron positron can give you both 1 and 2 showers. So this basically gives you the probability that such a signature gives a 1 shower. What is also relevant for this scenario in connection to the most recent results from MiniBooNE is the timing constraints. This is the neutrino bunch time. I took it from the recent MiniBooNE paper, and you can see the excess is shaped very similarly to the backgrounds, which means that these new physics events that we are discussing here should not be coming from a very heavy right-handed neutrinos produced in the source, because this n, while traveling, it's massive, so it's lower than active neutrinos, so there would be some extra delay coming from that. And basically, these timing constraints, recent one, impose that the right-handed neutrinos should not be more massive than the order 10 MeV. So the 100 MeV is too much. 100 MeV that works for the upscattering scenarios does not work for this decaying scenario, just from these timing constraints. The next scenario is the upscattering decay, UN, the Xi. It's the same as the previous one, just instead of mixing, you produce right-handed neutrinos from the muon neutrino interactions with particles in the detector, or in the medium between the source and the detector. So you can also produce it in dirt, so in the earth that is before the detector. So all of these things are in neutrino detectors happening underground. And here the total number of events is proportional to both neutrino fluxes and the cross-section that in this case enters in the calculation, and the total mass of the detector. In this scenario, basically, we considered the upscattering, as I said, in the dirt, as well as in various detector subcomponents. This will be relevant for the T2K near detector that I'll just discuss a few slides from now. And two of the aforementioned models belong to this class of scenarios. The first two that I discussed by Gninenko and Belet et al. Right. Going further, there is the upscattering into right-handed neutrinos, following by two-step decay, first in the boson and then in the Xi.
Excuse me.
Yeah.
May I ask a question? Are you saying that the not only the total number of the signals, but also the distribution, energy distribution, can also be explained by those scenarios?
You mean these theoretical models that I discussed, the people proposed previously? You mean these two slides?
Yes, but what I'm wondering is that the so MiniBooNE has a plot for the energy distribution with respect to the anti-neutrino electron neutrino at a detector, right? So
I didn't hear the sentence. Can you repeat it? The MiniBooNE has a what?
The plot you have shown in the very beginning.
Okay, yeah, sure. Yeah, so all of these models have a reasonable fit to the data. It's a matter of kind of, it's a matter of taste, how well it usually this first bin is never properly explained fully. But MiniBooNE also has the angular, the distribution of the shower. What is the angle between the incoming neutrino and the angle of shower? So the zenith angle distribution. But in this talk, I'm not going to discuss the zenith angle distributions, but several of these papers, dedicated searches, have considered that too. What is problematic in that case is that many of these events actually are kind of boosted. The distribution is such that the forward bin is most populated, and which means that most of these showers actually go in the direction that is not too much different than the incoming neutrino direction. So that has induced some problems for these scenarios. But it's really a kind of, in my opinion, some sort of a matter of taste. If you do a chi-square analysis and you get a certain value. So many of these models are also confronting problems with some tensions with other experimental data. But in what I'm going to show later, I'm going to try to make some model independent tests of various scenarios, but by not relying on particular couplings and mixings, these things would cancel.
I see. So at that moment, yeah. So at this moment, you're only assessing the models based on the total number, the total number of the events.
Yeah, in my analysis, we're only looking at the total number of events. One can, in principle, improve this by considering the angles, and then the different scenarios would might receive more strength constraints. But when you include the angle information, you know what? If you can just hold on, when I start showing the plots in maybe 2 or 3 slides, then it will be more clear. And I will come back to this question about the angle.
Yeah, thank you.
If you don't mind. So yeah, just to briefly, so I went through these 2. So just to briefly go through the reminder of these possibilities. Number 3, upscattering and double decay. So it's basically very similar to the previous one, where it's UN dxi. It's just that here there's the intermediate boson that gets produced and decays into xi. If this boson decays promptly, the calculation would be very similar. Actually, the expression would be identical to this contribution here. It's just that the signature factor for a fraction of 1 shower and 2 shower events when there is E plus E minus in the final state would be different, because here that is usually connected to the invariant mass and the angles, and in this case it will be controlled by the mass of B boson that decays into those particles, whereas here in this scenario it's the neutrino that does right-handed neutrino that does the 3-body decay. So the invariant mass would be a function of right-handed neutrino. Here's also the schematics for this kind of scenario. There are also these 2, 4 and 5, which I see as an option, but none of the models I discussed previously from the literature, none of the models employed these kind of realizations. So I'm not saying that it doesn't work. It's definitely an option, but the model building has not yet been done for these scenarios. So number 4 here is the upscattering into right-handed neutrino. And then this right-handed neutrino decays in the active neutrino, which in the detector scatters into the electron, just due to the interaction, the star model interaction. There might be some problems with the model building for this kind of realization, because you see 2 upscattering. There's two interactions that needs to happen, and this brings certain smallness. So building a model for this scenario could be challenging. The number 5 is mixing a decay, double decay scenario, which is basically equivalent to 3. It's just that the production is through through the decays of pions instead of from the interaction of right-handed neutrinos, and also the schematic representation. In my results, actually, I will not show anything about these 2 scenarios. They're probably very the constraints could be applied from the similar scenarios. For instance, 5 and 3 are very similar, just that the production of right-handed neutrino is different, so the constraint could be similar, but I will not explicitly focus on any of these 2. And in the first version of the archive paper, we also haven't elaborated on these, but now in the before the update, we're gonna put more explicit also discussion and formula derivation for these 2 mechanisms. But during this talk, I think I will not come back to these 2 possibilities. Then there's the final one, the mixing MD-NU-UE, which is mixing decay into NU-E scenario. That would match the previous discussed models by Dentler and the Gouveia that was proposed in the literature. So here N is produced through mixing, so from pion decays in the source. It promptly decays into electron neutrino, and then this neutrino just scatters in the detector, producing E plus electron or positron. This B that is produced from the decays of N can maybe also decay to a neutrino and antineutrino, which is essentially another source for a shower. So in that case, you could even explain the anomaly in an easier way. If n decay is small, n decay length is small, then the number of events here is simply proportional to the usual standard model charge current cross section, the total mass, the mixing parameters, and the flux of neutrinos. One of these two papers that study these scenarios, I'm showing their plots for the spectrum here for the reconstructed neutrino energies. And you can basically see that here the blue histogram, not the histogram, but the blue lines and the orange ones are very similar. The former corresponds to the 3+1 EV scale sterile neutrino, and the latter one is this scenario. In my first slide, I was discussing that 3+1 scheme does not work from the constraints point of view, but you see from the spectrum point of view, it's very similar to this scenario. So they give similar results, but this scenario here has more parameters and you have more freedom and hence is not excluded. It's also cosmologically much better because when you have sterile neutrino that decays, it can decay very early in the universe, so you don't have problems with extra degrees of freedom, of relativistic degrees of freedom at BBN or CMB. I should also mention that this scenario works for order KV scale masses. So in these slides, I'm basically discussing the strategy. It's very simple, and here you see that I will rely on the total number of events. I will not be discussing any angular distribution. So we basically want to employ the neutrino experiments to test these scenarios. So what we do is we take the MiniBooNE excess, which is here 638 events when summed in the both neutrino and antineutrino mode, and we multiply this by the ratio of theoretical ratios, including various cuts that appear in the experiment. So basically the theoretical ratio of the expected number of events for an experiment I and a given search. So that search can be 1 shower, 2 shower, or whatever. That's here in the numerator, and the denominator is the MiniBooNE number of 1 shower events, also theoretical calculation. So, and that gives us the expected number of excess events due to new physics that would appear in that detector, that detector I, the detector that we would be considering. So basically, by doing this, you assume that the new physics that you're testing is fully explaining the MiniBooNE, and then you're asking the question, okay, how many events, if really MiniBooNE sees 600 events, how many events is T2K gonna see in 2 shower search or in 1 shower search? So how many excess events should other neutrino experiments see? This is very simplistic, but in some sense, a very elegant, in my opinion, way to do things, because you see that in this ratio, mixing parameters, coupling constants, they all cancel. Most of the theoretical parameters just cancel. Admittedly, I'm coming back to your question from before. Here, it's only the number of events that is considered, and for testing, for improving the tests, one could of course think about including the angular information that MiniBooNE has performed, but we have not used that part of the data for the analysis. And then when we get to the number of expected events that be seen in some experiment, then we actually go to their respective paper, and from their plots see how many data was there seen and how many standard model events has been simulated. And using the systematical and statistical uncertainties and the data being distributed like a Gaussian, we can basically compute the upper limit on the allowed number of new physics events at a certain confidence level. And then it's basically just comparing 2 numbers, what you expect to see in a given scenario, and 1, 2, and 3 sigma limits on the numbers that should actually be seen. And then you can basically do this kind of comparison for any search, for any neutrino experiments, essentially. And those that I will be using are going to be T2K near detector, which has this structure of pion detector in front, which is very massive, which can be used for producing a right-handed neutrino in the process. And then right-handed neutrino can only later decay in these other subcomponents, which are time projector TPCs, time projection chambers here in orange, and the fine-grained detectors, which are in green, the two of them. There's also MINERNA that is used, NOVA. This is here a new detector on the picture. And there's also the old experiment, which is rarely discussed in the literature, PS191, which has reported certain excess of the electron-like events in their calorimeter. And this excess, I'm not sure how seriously it's taken in literature, but for me, it's interesting to think about whether MiniBooNE and PS anomaly can maybe simultaneously be explained. There'll be some plots on this experiment very soon. These are all overview of all the searches that we use. I'm not going to go through each of them, and this is also the list of all the parameters. So I said that many things cancel, but that's of course from the model perspective. The areas and the efficiencies and the lengths and the exposures for all these experiments that I want to confront with MiniBooNE is essentially different and enters in the calculation separately. So now I'm starting to showing the plots, and again, it's just showing the expected number of events for a given search in certain detectors using this formula, where this is are these integrated number of events, and this is the excess. So the first is for mixing decay. So producing right-handed neutrino through mixing and decay into a three-body final state with T plus E minus. And on the x-axis, you can see here the speed of light times the T0, which is the lifetime in the rest frame. So for the abbreviation, I'm just going to call this decay length, even though the real decay length in the left frame would have an extra energy over m factor. In each plot, there will be allowed at 1 sigma and allowed at 3 sigma. So if these lines of given predictions are above, then it's basically, for instance, here you can see that these three are disfavored at around 3 sigma, but still not exceeding the, at around 1 sigma, but still not exceeding the 3 sigma. In this left panel, I'm considering this T2K near detector 1 shower search. And in the right panel, it's the T2K near detector 2 showers search. You can basically see similar level of exclusions around 1 sigma at least. And also in the right panel, there's even 3 sigma in certain portion of parameter space for very small decay lengths, where there's this upturn of the prediction. That upturn can be understood from the expression for the event number that I discussed previously, and that's basically the exponential that tells you that basically the right-handed neutrino needs to travel from the source to the detector. The masses I'm considering here in this plot are around 10 MeV or smaller because of the timing constraints that I previously employed. One can of course use 100 MeV or so, but that would be excluded, both from the timing but also from this our analysis at T2K. What I didn't mention is this vertical line, which is basically going to be representing 1 sigma width of the MiniBooNE prediction. Basically, this number here, 638, that's the best fit, but in reality, that's 638 plus minus 130 or something like that. So this these vertical patches here in each plot is going to just show the 1 sigma uncertainty on the prediction based on the fact that MiniBooNE there's certain uncertainty in the MiniBooNE excess events. What is important information is that we're not doing any detector simulation here, and for the case of electron-positron in the final state, we use the invariant mass of that pair as a criterion for distinguishing between 1 and 2 showers. So for MiniBooNE, this invariant mass should be around below 30 MeV to have E plus E minus appear as a 1 shower. And for T2K, which is a better detector for resolving these things, we found from the literature that 5 MeV would be a reasonable number to put in the calculation for that. This is again the mixing decay scenario, but in this case, decay is just into gammas, not in 3 plus E minus pairs. And here you can see from the left panel again the near detector and MINERNA. Now I'm comparing to the limits inferred from the literature on single gamma showers. And here the new detector is deferring this scenario at around 1 sigma or so. It becomes better at when the exponential upturn happens. And MINERNA is even stronger than that, even about 3 sigma at decay lengths of around 10 to 100 meters. The reason why these decay lengths are between 10 and 10 to the 5 is because this right-handed neutrino really needs to travel from the source to the detector and then decay within the detector. So the lifetimes, the decay lengths of 10 to the minus 5 meters would not work because it would just decay too soon before the reading the detector, and you would not have any signature. But however, in these upscattering scenarios where everything happens in the detector, it's a completely different playground for these values of decay lengths. You see, this is all smaller or around the mass, so the length of the detector. So here I'm using this upscattering decay, which was, I think, labeled as number 2 among those 6. And the decay is again into E plus E minus pair. So you can have 2 tracks at T2K or a single track. For 2 tracks, we find quite a strong exclusion, mainly because there are there's 2 charged particles in the final state, theoretically, electron and positron. And we're looking for two shower search from. So basically, there's no any misidentifications. You're not paying any price from that. You're, for instance, paying a price when you search for 1 shower in near detector, because for right-handed neutrinos of the order of 150 MeV, only a small fraction of events would appear as a single track, a single shower in the T2K near detector. That's why this number is very big and this one is suppressed. It's simply just because of the signature factor and the fact that most of the events would appear as 2 showers. I said that many things cancel, and they really do. The mixing doesn't enter in the ratio. Mixing cancels, and all the coupling constants. But admittedly, for this kind of calculations, you need to put some shape of the cross section. And here we basically follow the prescription of 2 of the papers I discussed before of Bertuzzo and Ballet. First one is using coherent, and the second one incoherent cross section. So therefore, in all the remaining plots, I will be showing both coherent and incoherent cases. And in reality, you basically have both options. But in these 2 cases, for these 2 benchmark points that these papers are offering, there's one of them is dominant, either coherent or incoherent. So in principle, the realistic scenario could be somewhere in between. I'm showing here the 2 limiting cases. What is also relevant to mention here is that we're not making any cuts of the events that could induce some extra, the scattering that could induce some extra hadronic activity, and that could happen for incoherent scattering. So in the incoherent scattering, there could be some extra showers produced from the hadronic activity that might be vetoed, and those events could be discarded. So this is, in that sense, for the incoherent, is the most optimistic prediction. Whereas for coherent, there's no problem with these hadronic cuts because the coherent is usually not associated with any significant hadronic activity. Regarding PS, let me just briefly mention that this is for the same model, upscattering and then into right-handed neutrino and then decay into E plus E minus. This is the same as in the previous slide. You can see much less number of events because the number of protons on target for PS 191 experiment was very small, 2 or 3 orders of magnitude smaller than MiniBooNE, and in T2K also. So the strength for 2 shower search in PS is here not competitive to the near detector. As far as the 1 shower is concerned, you can see what is interesting is that for some of the masses, these are 35 and 25.350 and 250 MeV. These lines actually intersect the observed axis at 1 sigma that I discussed previously. But in this framework where there could be 2 showers, in this model where there are E plus and E minus in the final state, it's not that interesting because this seems to be already disfavored by 2 shower surge, in particular for the T2K that is more powerful. I'll come back to the excess of PS191 in one model where there wouldn't be possibility for 2 showers, but just a single shower in couple of slides. Now I'm moving on to upscattering and then decay in the gamma. Here on the left panel, there's the MINERNA, and then comparing to the limits from neutrino electron scattering search. You can basically see that this model is disfavored at least at the level of 3 sigma throughout the whole values of decay length of right-handed neutrinos. In our current, in the first version on arXiv, this has been even larger because at that point we haven't considered the important cut on this variable here, which collaboration uses to distinguish between scatterings on electrons and nuclei. So we there showed even stronger prediction, but even after properly taking this cut into account, the prediction is still very strong, and it's about 3 sigma. And for T2K, we can also compare to the gamma shower. I should also mention that this bump for T2K, the bump that was also present, for instance, in the previous in this slide, just forgot to discuss it. The bump at around 10 to the minus 1 is coming from the upscattering in the pion detector. So coming back to this, so you can produce right-handed neutrino by scattering in this pion detector that is very massive, and then the right-handed neutrino only decays after 1 meter or so when it enters in this active part of the detector, active volume. And that is basically the bump that is visible here and also on the other slides. The MINERNA seems to be stronger for this scenario. The T2K is at the level of 1 sigma, apart from this case where you can employ this pion detector and upscatter, and at that point you can even see such events that you approach the 3 sigma. Okay, and notice also that here there is something strange going on here in the shape. Usually the shape would be from the scattering detector, the shape would be like here in the previous slide for PS, that you have something constant for the very small decay lengths and also constant for the very large decay lengths. So, and there's some intermediate region. So this doesn't go down like in that plot because for MINERNA we estimated the scattering in the dirt. So this would basically be the contribution of production of right-handed neutrinos before the detector inside of the earth, which is mostly silicon and oxygen. And then these right-handed neutrinos would then go inside of to the detector and only decay into in the detector. It's useless if they decay right away there because then they would just be absorbed in the dirt, but they could still be produced in the dirt and then only decay somewhat later. And this is why this effect is important for larger values of right-handed neutrino decay lengths. Finally, one plot about upscattering and then double decay. Here, there's the constraint on MINERNA, which is very similar to the one on the previous slide, because MINERNA does not distinguish between, at least the search that we consider does not distinguish between E plus E minus final state and gamma final state. And also, upon properly taking into account this cut that I mentioned on the previous slide, our predictions are comparable to those by Argyris et al. That did a dedicated search for MINERNA. They basically did a detector simulation and found 3 sigma effects for disfavoring the MiniBooNE explanation of this type. That is Bertuzzo et al., what I discussed at the beginning of the talk. For the near detector here, you can basically see that there's again a bump coming from the pi detector. The situation here for the U decay into boson and then decay into E plus E minus pair is different than U and then directly decay. This is because of this shower criteria and the invariant mass. So in this case, your right-handed neutrino first decays into boson that I labeled here with 30 MeV. So it's 30 MeV boson, because simply I took the number that Bertuccio takes in their paper, and I think even larger values of boson mass are disfavored. At least their kinetic mixing is very constrained. So the invariant mass of the E plus E minus pair will basically be 30 MeV, around 30, whereas the invariant mass for this three-body decay of a right-handed neutrino that was, for instance, used in this plot here would be different. That's why the level of prediction is here different, and the signature factor for the two showers is different, even though all the remaining part of the calculation are identical. The signature factors differ. You can see that in this case, where you can use this upscattering of pi detector, you rise about 3 sigma. Otherwise, you're at the level of 2 to 3 sigma, essentially always larger than 1 sigma. The reason why I'm in this slide showing starting showing only from 10 to the minus 2 in decay length is because this doesn't really extend to 10 to the minus, very small, because the collaboration is able to, if the upscattering happens inside of one of the fine-grained detectors, the decay should not happen within that detector, according to their search, but only outside in the TPC. And if decay length of n is too small, then it would decay already inside. So those events with very small lifetime would be effectively vetoed. I see I'm running out of time, but I'm luckily on my next to the last slide, which is the scenario of mixing decay into nu E and then upscattering. That's that scenario number 6, which I argued to have very similar spectrum to the usual 3+1 scheme. And here we basically found the most relevant player to be NOVA detector, where the best fit at small values of decay lengths are disfavored at around 3 sigma. Whereas if you take this uncertainty in the MiniBooNE prediction into account, the NOVA and the MiniBooNE would be comparable at around slightly less than 2 sigma. To back this statement up, I'm putting here a plot that I found in a PhD thesis from NOVA, where they basically did a simulation and they found that around the 90% confidence level, which would be 2 sigma, the NOVA here, which is red without systematics, with systematics, and this black one without systematics, is excluding good portion, almost everything of the MiniBooNE prediction. This is kind of mixing on the first side apples and bananas, with different stuff, different models. But I argued before that the spectra for the usual 3+1 model with electron volt sterile neutrino and this case here are very similar. So the tests should also be rather similar in that respect. I promised before that I would briefly come back to this PS191. Unfortunately, it's lying slightly below the excess at 1 sigma. So in that sense, this scenario does not offer for a simultaneous explanation of MiniBooNE and the PS anomalies, but instead the take-home message is that NOVA is the most relevant player here. For NOVA, there's usually some I think NOVA is kind of struggling with their backgrounds, and so it's also relevant. What do you take for the systematic uncertainties? I guess we were on the generous side, putting only 15%. So that could also impact the level of at which NOAA can basically test this scenario. But the NOAA is in principle sensitive because it's a detector with a very big fiducial mass and big exposure, and it's continuously running. So it's going to be interesting for the future. And then let me summarize. So the idea here was to study a model-independent, in a model-independent way, the non-oscillatory explanations of MiniBooNE. The idea was, so there were several papers in the literature, and we wanted to basically make some systematic study and make an effective theory of MiniBooNE to see what are really the options that could be employed. And after doing this, after organizing these scenarios, we went further to perform tests, and basically our master formula was that simple ratio of a number of events, where we basically take, okay, we explain the MiniBooNE, we put in 600 plus minus 1 sigma deviation, compute for each of the searches that we're interested in. For the neutrino detectors, we compute the number of events and see how many events T2K, MINERNA, PS, NOVA should see in that model framework that explains MiniBooNE. Then this can be compared to the sensitivity of these experiments, and you can set limits at a certain level of significance. In that way, you don't care about really what are the model parameters, kinetic mixing, neutrino mixing, couplings. So this is on the positive side. But by saying that, I'm not saying that it's useless to focus on one particular model. That's also very good when tests of one particular model are, for instance, performed by searching for, I don't know, kinetic mixing and setting the limits and narrowing down the parameter space. These are also valuable studies. And the flow of the procedure that I described was that I haven't admittedly taken into account anywhere the angular information. This is something that could in principle be included in some more general analysis. And the conclusion is, as I led you to the several of these realizations, so I think in the plots we passed through 4 out of 6 models. Each of them were tested, and portions of parameter space disfavored using at least using at least one other neutrino experiment. So my final conclusion is that I think the model-independent way of testing the MiniBooNE must come from the neutrino physics itself. Particular models you can constrain using kinetic mixing arguments, or but this kinetic mixing can if you disfavor something, some z prime, you can always give up on the kinetic mixing, put a scalar instead of z prime, and save the situation. Or and this is what some recent models have actually done. So yeah, I'm basically saying that model-independent tests should be coming from the neutrino physics. And if MicroBooNE, that is now operating and discussed for solving the MiniBooNE anomaly, if MicroBooNE will not deliver, the ultimate test of MiniBooNE, then we're going to have to wait and I would say chiefly rely on the other neutrino physics experiments to see this, to assess the MiniBooNE and to see where it will lead. Is this anomaly going to be confirmed in some portion of parameter space or totally ruled out? I think these neutrino experiments will play a significant role in the near future. While PS is not running anymore, T2K detector and NOVA, these are experiments that are continuously accepting more and more data, and there have been also MINERNA, so there have been new talks and updates in the recent neutrino conference. So I would say that the future on this side is bright when it comes to testing the MiniBooNE realizations. I think this is it. So I'm open for questions. Thanks for listening.
Thank you. Okay. So questions.
So, hi, thank you for the nice talk. And in the beginning, you described several models for MiniBooNE access, and which models are, favored or disfavored by your model independent analysis?
So basically, all of these models that were proposed here, I have explicitly or implicitly discussed constraint here. But if you're just asking which of these models would be favored or unconstrained, I would probably have to say that this is the models that were recently proposed by Datta et al. And Dutta et al. Which is basically the realizations of this model here, the upscattering into right-handed neutrino, then decay into bosons. So this two-step process. And that would basically be this slide here. So you see that MINERNA is effectively disfavoring this model with Z prime, and that was found in this paper. But these guys, these two groups, have replaced Z prime with a scalar. And in that sense, MINERNA limits are not applicable anymore because the cross-section dependence of the upscattering to scalar is just such that the cross-section drops at higher energies. MINERNA peaks at around 5 MeV, which is factor of 5 bigger than MiniBooNE. So you can forget about MINERNA limit for those cases. And the NIR detector would also not efficiently probe those models if the decay length is very small. So if it's smaller than 10 to the minus 2, then it doesn't apply. If there are realizations in parameter space around 10 to the minus 1, then this NIR detector is also constraining. I said that there's a sharp cut here at 10 to the minus 2, around 10 to the minus 2 in the decay length meters, because the search of T2K is such that when you produce right-handed neutrinos in the detector, it needs to decay already within that fine-grained detector. Sorry, it needs to leave the fine-grained detector and decay in the time projection chamber, which means that it needs to travel for some time. So I would say that the safest option at the moment, as I see it, is this kind of realization with scalar. If in the portion of parameter space where right-handed neutrino decays very promptly. And in that case, none of these two plots would be constraining those scenarios. So that's my answer. I would probably vote, at the moment, I would probably vote for one of these two very recent approaches.
Okay. So thank you for the explanation. But I think you mentioned, but I forgot. So what is the main difference between the scalar instead of G prime?
So it just turns out that you can, for instance, this paper here shows a very nice plot for the cross section. So you basically so in the case of Z prime, the cross section grows around the energy of MINERNA, which is 5 GeV, where MINERNA has a. Unfortunately, I don't have here the fluxes of MINERNA, but they peak around 5 GeV. So the cross section in Z prime grows in that range, but the cross section when there's scalar mediation drops there, and therefore it makes it much less relevant for MINERNA.
Okay, thank you.
Okay, so other questions? I have one question about the decay length. The ND280 80 even figure.
You mean what this means here, or?
No. The decay length. You next. I think the next. This page 14.
14.
Yes. In this plot, the MiniBooNE, the vertical line exists in the 10 to 4 decay length corresponding to a 10 to 4, or is quite should.
Oh yes, sure, of course. But you know, you can have, you know, if decay length is much bigger than the baseline, then you know, you would still have certain portion of these neutrinos decaying around 10 to the 2 or whatever is the baseline, around 100 meters for these experiments, but it would lead to a certain suppression. So this can be, for instance, compensated by larger couplings, or you increase the branching fraction for the right-handed neutrino production from pion decays, for instance, or kaons. But in principle, I know that the model that was proposed, and that's this one here, just to show you the archive number, 1909, used this mechanism, and they used it worked for 10 to the 3 in C tau, 10 to the 3 meters. That was what they considered there. So there is many of right-handed neutrinos would just pass, but some would still decay within the detector, and that could give the explanation. It's just that this model is actually excluded already for the reasons I mentioned before. They just considered too big masses, too large masses, whereas the timing information, where they put this timing information that is only now available, is basically telling you that in these scenarios with mixing, where right-handed neutrino has to travel for quite some time, you simply you know, you need to have it rather light, smaller than 10 MeV or so, because otherwise this figure here, the excess would be much distorted with respect to the usual neutrino signature, simply because of the greater delay and the longer traveling time. So the answer is it could work for larger. So we didn't put any parameters for the couplings or particular scenarios, but just use the ratios and extended this plot. So it's on the model building side if you want to build a model, but in principle, if you can build a model and with the couplings that are not excluded, this is how it would look for 10 to the 4. You see at some point it starts to flatten because the exponential that appears here would basically go to a constant value. This lambda n would basically be this C tau times energy over mass. So yeah, we wanted to be model independent by putting C tau and then allowing many different numbers. But if one wants to take a model, then of course for given couplings and the branching ratios of pions or kaons into right-handed neutrinos, then there would be some of this C tau preferred, or you can cook up something around 10 to the 2 or 10 to the 3 or so.
And another question is if we consider the supernova neutrino.
Sorry?
Supernova neutrino.
Oh, supernova neutrino.
Then they near the core, or there might exist some interaction like obscuring process. So
but you know what is the problem with supernova neutrinos? I'm here discussing, and what explains MiniBooNE, you see here in mixing decay, it's 10 MeV or lighter, and in upscattering, it's order 100, 200, 300 MeV. So these kind of states are too heavy to be produced in supernova, right?
Oh, okay.
maybe marginally you can produce these 10 MeV states. Okay, here I even put 2 MeV. But I wouldn't expect supernova to be a crucial, too relevant for this for MiniBooNE, because it's simply new physics at around typically tens to few hundred MeVs that is required.
Thank you. So, any questions?
Excuse me, I have one quick question. This is just out of my curiosity, but in the models involving the right-handed neutrinos, is there any relevance depending on whether the neutrinos, right-handed neutrinos, are Dirac or MINERNA fermions?
From the model building perspective, I'm not so sure, because these scenarios, they're purely phenomenological. But in principle, I don't see what would be a problem if it's also Dirac. I usually always assume these states to be MINERNA, but if a Dirac state can also have the same decay channels, I don't see a problem for MiniBooNE.
Yeah. What I was wondering is that if it is MINERNA and if right-hand neutrinos are participating in a seesaw to give a mass, there's a constraint from the neutrino subrotator decay, the constraint on the mixing angle.
That's true.
And if it is MeV scale, maybe the mixing angle should be smaller than like 10 to minus 5 or something. I don't remember exactly. But
that's true, but remember that the constraint from neutrinos double beta decay is on the mixing between sterile and the electron flavor.
Yes.
But here you have this kind of acceleration-based neutrinos. They're dominated by the muon neutrino fluxes.
Oh yeah,
so
yeah.
This is basically another mixing that takes part.
I see. Yeah, that's true. All right, thank you.
Okay. Any questions? Or there's no more question. But I have some simple question. Did you consider some kind of smearing effect in your analysis, or
Which kind of effect?
Smearing effect, like some.
Smearing
effects. Okay. Smearing effects. No, we actually haven't included that in the formulas for the event rates, even though they're quite involved. We haven't used that. We implicitly using such information when looking for these upper limits on the allowed number of new physics events, because all this data in principle has this included. I would not assume this to be very drastic, but in our theoretical formulas, for instance, for this ratio, this was not included. This would be an extra integral over Gaussian, and it's not included.
Okay, thank you. So, any other question? think there's no more question. So thank you very much, Dr. Vedran Brdar, for the very nice talk.
Thank you for inviting me.
Thank you very much.